Welcome everyone to today's Explainer Masterclass, where we are going to be tackling the fascinating and honestly super dual nature of ozone. If you're joining me in this college-level deep dive, go ahead and grab your notebooks, because we are looking at one of the absolute most misunderstood chemical compounds in our sky. I mean, ozone is literally the Dr. Jekyll and Mr. Hyde of our atmosphere. In one environment, it's our ultimate protector, an absolute necessity for any life to exist on Earth. But in another, it completely flips and becomes this toxic, suffocating pollutant. So how on earth can one single molecule play both the hero and the villain? Well, that is exactly what we're going to unpack today.
Here's our syllabus for today. First, we'll meet the molecule. Then, we'll explore the good protector, followed by its alter ego, the bad pollutant. After that, we'll examine the ozone hole, look at the environmental fallout, and wrap things up with a quick pop quiz.
Section 1. Meet the molecule. Let's start with the basic chemistry. So ozone isn't your standard, everyday oxygen. It's a highly reactive triplet that eagerly interacts with other compounds. You know the oxygen we breathe in every second of the day to survive? That's O2, two oxygen atoms, perfectly paired up and incredibly stable. But ozone is O3. It's got that third wheel, that extra oxygen atom, which basically makes it chemically unstable. And because it's so unstable, it's constantly looking to react with other molecules around it. That right there is the exact trait that gives it its Jekyll and Hyde properties.
Now, this unstable O3 molecule really likes to hang out in two main locations, the stratosphere and the troposphere. The stratosphere is our upper atmosphere, way above the clouds. The troposphere, on the other hand, is the lower atmosphere, basically from the ground where we're standing right now up to about where commercial jets fly. And here is the kicker. Where this three-atom molecule decides to exist completely changes how it interacts with life on Earth.
Section 2. The good protector. Let's look at stratospheric ozone.
Think of this upper layer as Earth's ultimate pair of sunglasses, protecting absolutely all life by blocking 95% of harmful UV rays. Naturally, way up in the stratosphere, the sun's intense UV radiation actually splits stable O2 molecules into single, lonely atoms. Those atoms then crash into other O2 molecules, bonding together to form our O3, ozone. It blankets the entire planet, and without this giant pair of planetary sunglasses, the sheer volume of solar radiation would make life on the surface literally impossible.
So the absolutely crucial point here is understanding exactly what those sunglasses are protecting us from. The sun throws a few different punches at us in the form of UV radiation. UVC is the heavyweight, the highest energy and by far the most dangerous. Thankfully, our stratospheric ozone almost completely blocks it. No way that's getting through. Then we have UVB, which is highly harmful but heavily filtered by the ozone layer. Finally, there's UVA. This is the one that slips through the most. If you've ever gotten a sunburn from hanging out on the campus quad without sunscreen, yeah, UVA is largely to blame for that. It causes tanning, premature wrinkles, indirect DNA mutations, and it's a leading cause of most skin cancers. Now just imagine if the ozone layer wasn't there to block the UVB and UVC. Our skin health safety wouldn't just be at risk, it would be practically non-existent.
Section 3. The bad pollutant. Welcome to the Mr. Hyde portion of our lecture.
Down here in the troposphere, bad ozone is a really harmful air pollutant, and it's a major component of the smog you might see hanging over a city skyline. Unlike the ozone created naturally by solar radiation high above us, this ground-level ozone is completely human-made. It's the direct result of volatile organic compounds and nitrogen oxides mixing together and just baking in the sunlight. This isn't a protective shield anymore. It's a toxic bubble. It severely irritates our respiratory systems and heavily worsens conditions like asthma, which is especially dangerous for kids and the elderly living in dense, local urban areas.
To really clarify the contrast here, remember that the good ozone is natural and way high up, while the bad ozone is a lot like toxic car exhaust brewing right at street level. And you know, this brings up a massive debate we constantly face in environmental science. How do we balance necessary industrial growth with environmental protection? The precursors to this bad ozone come directly from fossil fuel combustion, our cars, our power plants, our factories. We absolutely rely on these for our economy, right? But at the exact same time, they are directly responsible for creating this dangerous ground-level smog. It's a tough balancing act.
So to perfectly map out this Dr. Jekyll and Mr. Hyde situation, up top in the stratosphere, good ozone gives a massive thumbs up, blocking incoming UV radiation. But right down where we live, breathe, and commute, bad ozone reacts with emissions from industrial smokestacks and tailpipes, resulting in a toxic thumbs down. Two identical chemical compounds, O3, with completely 100% opposite impacts on our survival.
Section 4. The ozone hole. Let's examine what happens when our shield breaks down.
We very often call it a hole, but honestly, it's a lot more accurately described as a severe thinning that allows dangerous UV radiation to pour through, especially over places like Antarctica. It's not like a literal physical tear in the fabric of the sky, but rather a really drastic reduction in the concentration of those O3 molecules. And when this layer thins out, those dangerous UVB and UVC rays we talked about earlier, they suddenly have a much clearer, faster path straight down to the surface.
Now, this destruction isn't just random. It is a highly specific, three-step chemical chain reaction triggered by our own use of manufactured chemicals. Step 1. Humans manufactured and emitted what are known as ozone-depleting substances, or ODSs. The main culprits here were chlorofluorocarbons, CFCs, which we heavily used in refrigerants and everyday aerosol spray cans. Step 2. When these CFCs inevitably drift up into the stratosphere, they release highly reactive halogen gases, specifically chlorine and bromine. And Step 3. These halogens act like absolute chemical wrecking balls. They catalyze a continuous, repeating chain reaction that aggressively rips O3 molecules apart, turning them back into regular oxygen. They essentially delete our protective shield faster than nature can rebuild it. This terrifying process is exactly why global regulations, like the famous Montreal Protocol, were eventually established to aggressively phase out these specific chemicals.
Section 5. Fallout. The very real consequences of this chemical interference.
What we're seeing is a vicious cycle where industrial emissions deplete the ozone, which in turn scorches our ecosystems and actively alters our climate. On one hand, our heavy industrial footprint pumps these ozone-depleting substances into the air. And then, as the protective layer thins, increased UV radiation just hammers the Earth, causing widespread, devastating ecosystem damage. It's an entirely unnatural loop of our own making. Whether it's the direct threat to your own skin health, or the completely invisible damage to the phytoplankton that anchor the entire ocean's food web, the fallout is massive. For humans, more UV means skyrocketing rates of skin cancers, cataracts that can actually blind us, and even the suppression of our immune systems. And for the environment, it is just as brutal. Plankton in the ocean die off, starving marine life. On land, increased UV decreases photosynthesis, meaning our agricultural crops yield far less food. And ironically enough, more UV radiation hitting the lower atmosphere actually increases the creation of certain types of pollution right down here where we breathe. This is exactly why making practical lifestyle changes, like actively reducing our individual chemical footprint, being really mindful of the refrigerants and aerosols we purchase, and supporting the reduction of fossil fuels is so absolutely crucial.
Section 6. Pop quiz. Time to see how much of this explainer you've retained. Think back to our chemical chain reaction discussion for this first question. What were those specific manufactured substances?
Spot on if you remembered CFCs, which release those destructive halogen gases. It was the everyday convenience of hairspray cans and cooling systems that inadvertently triggered a total global environmental crisis.
Remember our analogy comparing this pollutant to something you encounter in heavy city traffic? What's baking in the sunlight to cause this?
That's right, the burning of fossil fuels mixes with sunlight to bake into toxic ground-level smog. It's a stark reminder of how our daily commutes and our energy usage directly impact the air quality right outside our windows.
For our final question, let's look back at the energy spectrum of the sun. Which one is the absolute heavyweight?
UVC is the answer. But honestly, this leaves us with a pretty provocative thought. If our everyday chemicals can literally punch a hole in the sky, what other invisible systems are we altering without even realizing it? We've learned today that a simple chemical compound like O3 can be our greatest protector or a toxic threat, depending entirely on human influence. Thank you so much for joining me for this masterclass on ozone. Keep asking those big questions, keep examining your own footprint, and I will see you in the next explainer.